not Boris. But better looking than Boris, right?
Yeah!
Yeah, thank you. Alright, so our next speaker is a British scientist, and he built one of the world's largest contextual search engines, Wolfram Alpha. Hands up if you've heard of that. Pretty good, pretty good. And if you want to find out more information about him, you can actually find out through one of the applications that uses Wolfram Alpha, which is Siri. So, Siri, who is Stephen Wolfram? I think she's prejudiced against British people. Well, he's moving in a new direction. He's going to talk to you about his latest work. So, Amsterdam, please help me welcome to the stage, Stephen Wolfram!
Well, so I wanted to talk today about sort of the big ideas about computation. And I myself have been involved in trying to sort of work out the implications of computation for about 30-something years now. There are several sort of very visible pieces of what I've tried to do. What I'll talk about is a few of those visible pieces, and then maybe say some things about sort of the general picture. So the three sort of most visible pieces that have emerged from at least my thinking about computation have been Mathematica, it's now about 25 years old, Wolfram Alpha, which came out about 4 years ago, and A New Kind of Science, where the big book was published about 10 years ago. So I'll talk a little bit about those things and about sort of some of the things that are now emerging. So probably the most immediately visible sort of manifestation of computation as I see it is Wolfram Alpha, and probably mostly seen sort of the basic idea here. The notion is Wolfram Alpha has sort of a very ambitious overall goal. The goal is to sort of take all the knowledge that has been accumulated in our civilization and make it computable. What do I mean by that? What I mean is, if there's a question that can in principle be answered on the basis of knowing systematic knowledge, then make it automatic to have that question answered. Usually, you would imagine you have to go to some human expert to find the answer. The idea is, if there is a human expert who can answer it, make it automatic to get that answer. So that's a challenging, sort of difficult thing. We can go and ask Wolfram Alpha all kinds of things, like let's say, I don't know, let's ask it for the GDP of the Netherlands. How about that? And so its goal is both to tell us the specific answer, and then to sort of give us information that it thinks we might find useful on the basis of the question that we asked. So I could say GDP of the Netherlands divided by Belgium or something. And now it can understand, just as we as humans can understand what that input means, so can it, and it then gives us a result. Or we could say something like, we could ask it, what's if we combine the colors red and yellow, what will we get? And it will then go and compute that and give us an answer, tell us all sorts of other things about that color, and so on. Or we could go, we could say something like, where is the ISS, International Space Station? And now it will do something where it's kind of combining data that it's getting with the real-time feed together with computation to work out where that spacecraft is right now, and it will tell us it's currently below the horizon from Amsterdam, and it will next rise at 2:08 p.m. and so on. Well, there's lots of things that Wolfram Alpha can do. Kind of our goal is to sort of get any kind of systematic knowledge encoded in Wolfram Alpha. So if I type in a piece of the human genome, for example, it'll go off and figure out where on the human genome is a match to that particular base pair sequence. Or I can go and do a thing that's real popular. We see sort of waves of this every day around the world. You can do sort of any kind of math that you might be interested in, and it will just go ahead and compute the answer. Well, so the scope of Wolfram Alpha is pretty broad, and it's sort of an impossible, huge project. One might ask, how does it basically work? There are really four components. One is you have to have data about all kinds of things, and we've gone to sort of the primary sources of all kinds of data. It's not something where you can forage this data from the web. There actually just isn't enough data on the web to be able to get all the things we need. And also, it's something where we really want to have the data in a very clean form where we can actually compute things from it. So the second sort of step is, people don't typically just want to retrieve one number, they want to answer a question, which means they have to actually do a computation from the underlying data. So for that, one has to sort of encode all the methods and models and algorithms that come from science and engineering and financial analysis and all kinds of other areas to actually be able to compute specific answers. Because what Wolfram Alpha is always doing is, when you type in a question, it will just go and custom compute the answer to that question and custom generate the report. It's not going and searching for some place on the web where it can find the answer. It knows lots of things and can actually go and compute answers fresh for whatever you want. So the third issue is, how does it understand what you're asking? And for that, it has to be able to understand lots of natural language. And we've made some really big breakthroughs, I think, in understanding natural language. We have a tremendous advantage over all the efforts that have gone before in understanding natural language, which is that we have this huge supply of knowledge that we can use to kind of understand what the language means. So that's been an important area. You can use the linguistic capabilities of Wolfram Alpha right now. They're primarily used to find knowledge. You can also use them to, for example, perform actions, to ask some device to do something, those kinds of things. That's sort of a coming attraction in the future. So that's sort of the rough picture of Wolfram Alpha. I might mention that Wolfram Alpha is not just something that takes linguistic input. It can take other kinds of input too. So, for example, you might feed it, let's say we feed it an image as input. It can then go and compute things about that image, or we can ask it questions about the image. We could ask it natural language questions that can be answered by looking at this image, and it can then go and do those kinds of things as well. So okay, so how does Wolfram Alpha actually work? What is it inside? Well, it's built on a system called Mathematica, which in turn is built on what we call the Wolfram language, which is a new kind of computer language, except that actually it's 25 years old now. But the idea of the Wolfram language and of Mathematica, the system that's built on top of it, is to have sort of all of the algorithmic functionality that one can imagine sort of built into a single language, a single system. Now, Mathematica, as many of you may know, is pretty widely used in the world. Pretty much any R&D group at any sort of substantial company will have at least some Mathematica being used. It's been used in inventing and discovering all kinds of things over the last 25 years. It's pretty widely, it's used at pretty much every large university in the world and so on. But sort of the idea of the Wolfram language, which is what Mathematica is based on, is something a bit different from traditional computer languages. In traditional computer languages, one has sort of a set of fairly low-level operations built into the language, and the language takes the most pride in kind of structuring programs that get built, and maybe there are libraries that are added onto the language and so on. In the Wolfram language, the idea is that all of this algorithmic functionality is built right into the language. And it's something that's been a huge effort on my part and so on to maintain a kind of a coherent, unified structure for the language over the course of the last 25 years. And by maintaining that kind of unified structure, it's been possible to build sort of bigger and bigger building blocks in the language. So now, when we're adding a new capability, a new algorithm to the language, we get to sort of coherently build on all the other blocks that have already been put there. Another kind of idea of the language is to automate as much as possible. So sort of the user specifies what the objective should be for a particular computation, and then there may be 100 algorithms that could be used to actually perform that computation. Our sort of job is to have the right meta-algorithm that can figure out which of those 100 algorithms to actually use in a particular case. So I can show you just for a minute, just show you the Wolfram language sort of in action, hopefully. So we can go ahead and let's start off with some completely trivial computation. Okay, that's good, that works, that's a good sign. So we could say, for example, we could do something sort of simple, mathy kind of thing. Let's say, you know, make a plot. Let's say we make this, we sort of create a user interface for this. So we say, manipulate this plot with some parameter here. Let's do this. So now what should happen, we get a version of the plot that we can manipulate like that. Actually, we've also got the whole thing sort of integrated with Wolfram Alpha. So if I say something like, plot a sine curve, it should go off and use the Wolfram Alpha linguistic engine to go and figure out what that means and essentially synthesize the code automatically for that plot. Or if I say here, add a purple frame, it should go and synthesize the code for that from this natural language, and there's the actual Wolfram language code for that computation that's been synthesized by going off to Wolfram Alpha and asking for it. So you can do all kinds of things. You can manipulate all sorts of stuff. One of the big points about the Wolfram language is that it's symbolic, and you can have kind of any kind of symbolic structure be used within the language. So, for example, I could do something like this, where I'm just sort of nesting, framing some kind of thing. Or let's take a different type of object. Let's say I take an image. Hopefully, let's see if this works. So we should. Yes, there we go. It's a little bit blurry, but there's you all. Now let's take this image and let's say something like image adjust that image, and now we can actually put the image right into the. That was very exciting. Let's do an edge detection on that image. Okay, it's not too much of you there, but we could maybe let's do this. Let's ask it to find the current image and then dynamically edge detect the current image. So now we should have something which, if I put my hand in front there, it's actually doing the thing in real time. Kind of one of the ideas also in the Wolfram language is sort of everything is built in. So all of these algorithmic capabilities, also all sorts of things about data. So for example, if I say, give me a list of the countries in Europe, there's the answer. Or for example, I might say, show me, let's say, show me the shapes of the countries in Europe. And now I might take this, and now I'm writing a little piece of code here, go and do that. And there I've got the various shapes of countries in Europe, and I can go and manipulate them however I want. So kind of this is the idea of this language, is well, it's got all of this algorithmic capability and all of this knowledge built in. And so what is Wolfram Alpha? Well, Wolfram Alpha is basically 15 million lines of Wolfram language code, plus some number of terabytes of raw data, plus a whole collection of real-time feeds feeding in information about the financial markets, the position of aircraft in flight, the earthquakes, all sorts of other things. Well, so one of the things that's perhaps interesting that's coming now, the Wolfram language and Mathematica have for a long time been desktop products. With obviously Wolfram Alpha as a cloud system, one of the things that's happening is sort of the merger of those two things. So for example, this kind of will allow the Wolfram language to get deployed in a much broader way. So for instance, let me see if I can show you something which I realize I didn't prepare properly here, but it's okay, it should work anyway. So this is now a version of what we call the programming cloud, which is a version of the Wolfram language that is operating completely on the web. So this is just in the cloud. We can say something like this. And what's perhaps most interesting about this is the way that it's deployed. So these kinds of things, this is just operating in the web browser and doing its thing and so on. What you can do is essentially just press a button to create an instant API. So if you've got a little piece of Wolfram language code that does some piece of image processing or something like that, you just press a button, it generates an API, gives you a URL, you can call that thing from inside any other website or application. And similarly, we're going to have things where within any kind of language, you can go and basically just ask for a place where it will call out to either our cloud or your private version of that cloud to get Wolfram language capabilities and sort of all the Wolfram Alpha data stack and so on. So this same thing, it's going to work on desktop servers, in the cloud, also on mobile, and part of what's being done there is to use what we call CDF, our computable document format. And the idea of CDF is you can, I showed you moments ago, kind of a simple form of interaction. You can create a user interface interactively using the Wolfram language, and then that user interface can be deployed as in a computable document that you can then either put using a browser plugin, sort of at full fidelity on the web, or use Cloud CDF to have the sort of a front end on a pure website, and then the back end working in the cloud, or you can put it on mobile and have the thing be completely running natively on a mobile device. So that's some of what's coming there. There are sort of many pieces to this technology stack that we have. Another sample. Well, one thing that's kind of fun actually in Wolfram language right now in Mathematica, one of the things that's perhaps interesting is this kind of predictive interface that you get here, where given a result, it's trying to guess what would you like to do next. And actually the way it knows that is in part through the fact that we've seen billions of queries in Wolfram Alpha, and we've been able to figure out what do people typically do next. We're also able to kind of look ahead and use heuristics about which of these computations that we try doing as sort of a preemptive thing, which of these computations is likely to lead to the most interesting answer. So that's kind of something you get by combining several pieces of our technology world together. Well, other things that are another piece of our technology world is a thing called System Modeler. It's a system for doing large-scale systems engineering, so people who are making airplanes, boats, whatever else. You can have sort of encode the 50,000, 100,000 components that exist in those kinds of systems. What gets really interesting is when you can combine the simulations that we can do in System Modeler. What's coming in the future is the ability to take sort of a simulation of a complex system and be able to basically ask linguistic questions about the behavior of that system to, for example, a Siri-like thing or something like that, have the computations about the actual simulations of that actual device done in the cloud using System Modeler technology and so on. Well, okay, so this is something of the sort of technology stack in Wolfram Alpha, Mathematica, Wolfram language, and so on. Actually, a lot of this is connected to a big direction in science that I was interested in, that actually was the thing that caused me to start developing Mathematica and so on. And it's also something that's sort of very fundamental to the idea of computation. So let me talk a little bit about the science that I've been interested in. So kind of the starting point is, how do you understand, for example, the natural world? Well, 300 years ago there was this big idea from Newton and people like that we can use mathematical equations as a way to describe the natural world. And that's been a very successful paradigm. It's brought us most of modern science, it's brought us all sorts of engineering and so on. I got interested in what one can do to sort of generalize that paradigm. And what I realized was that you can go beyond kind of the rules that are defined in mathematical equations and sort of deal with arbitrary kinds of rules of the sort that exist in things like programs. So then the question is, well, what kinds of programs might nature actually use? It's probably not going to use the kinds of programs that we write for particular purposes that are thousands or millions of lines long. It's probably just going to use very simple programs. So then there's sort of the basic science question, what do simple programs typically do? So quite a few years ago now, I tried to start answering that question. I looked at some very, very simple programs. So here's an example. It's a thing called a cellular automaton. It's just got cells that are either black or white, and then at each step, the color of a cell is determined by the colors of the cells above it. And there's a simple rule. Effectively, the thing at the bottom there is the program for generating this pattern. Well, you can try different programs, and you get slightly different patterns. There's another simple program, corresponding simple pattern. Slightly different program, you get a slightly more elaborate pattern. Continue that, running that program for a while, you get this fine, rather intricate, nested pattern. It's intricate, but it's still extremely regular. So the question is, if you look out into the sort of computational universe of possible programs, does everything work like this? Does everything sort of have the property that with a simple enough program, the behavior that you get is somehow has a certain kind of regularity that reflects the simplicity of the program? Well, you can do an experiment. You can just look in the space of possible programs and see what all of them do. And you sort of turn a computational telescope out into this computational universe and see what's out there. Well, you see all kinds of different things happen. Each one of these pictures is a different program. My all-time favorite is Rule 30. And if we look at in more detail at what Rule 30 does, is what it looks like just starting from a single black cell at the top. We continue it a little longer, this is what we get. So you can see there's a certain amount of regularity over on the left, but this is a pretty complicated picture. And one might, when I first saw this, I kind of assumed, well, there's such a simple rule, there must be some hidden regularity that I'm not seeing. But a few years later, and lots of math and computer science and cryptanalysis and so on later, realized, no, this is actually a fundamental phenomenon, that even though the rule for the system is very simple, the behavior that it produces can be very complicated. And it turns out that that idea is something that is very robust, very general. It's a very common phenomenon in this computational universe of possible programs, and it's something that is important in understanding, for example, the natural world. There are lots of kinds of systems in nature. You take a snowflake or something, you can find that there's a very simple program that governs the overall structure of the snowflake. You look, for example, at systems in biology. You can find the same kinds of thing. You look at the mollusk shells, for example, you see all the elaborate patterns that they make. Turns out that those, again, can be described by these very simple programs. In fact, you can even be more ambitious than that. You can say, it's sort of a thing which changes one's worldview, one's paradigm about how things work, that even a very simple program that you sort of find at random in the computational universe can produce extremely rich and complex behavior. And that's something that it kind of goes against our everyday intuition, because our everyday intuition comes from things like engineering, where it usually takes us a lot of effort to make something complicated. Here in this computational universe, where we're sort of free of the constraints of sort of the history of human engineering, we're able to very easily produce very complex things, and that seems to be kind of the secret that nature uses to do that. So an obvious kind of big question would be, okay, if that's sort of happening all around nature, what about our whole universe? Is it possible that our whole universe comes from some very simple rule that can be could be found in this computational universe of possible universes? So let's see if I can show you a picture of that. So for instance, one of the things one realizes, if one's going to actually have a very simple rule that governs the whole universe, is that rule has to sort of operate underneath the level of things like space and time and the other things that are familiar to us. And so a reasonable hypothesis, and sort of its equivalent to other ones, is to start with sort of a universe where all there is a bunch of nodes connected together in a big network, and sort of what emerges in a very large scale is the structure of space and so on that we're familiar with. And so one of the things that one can do is to ask, to sort of look at this computational universe of possible universes constructed in this way and see, do any of them sort of correspond to our actual universe? And a lot of them sort of obviously don't correspond to our actual universe, but the interesting thing is that even among the fairly early numbers of possible sort of universes in this computational universe are things which are quite possibly actually our universe out lurking. So that will be an exciting thing if it turns out that sort of out in this computational universe of possible simple programs, there's actually the program for our whole universe, and that will sort of be an exciting moment in science and so on. One of the things that comes out from this is sort of that's an endpoint of science, but one can also use this sort of idea of the computational universe for technology. And perhaps the most interesting thing there is to kind of search the computational universe, mine the computational universe for things that are useful for technology. I mean, we're used in the physical world to going out and finding, liquid crystals or ferromagnetic materials or something like that, and then discovering that we can harness those particular physical systems for our technological purposes. Well, you can do the same kind of thing in the computational universe, harnessing things that you find, sort of algorithmic structures that you find in the computational universe, and using them for practical technology. And in fact, we do this all the time. In building algorithms in the Wolfram language, particularly in Wolfram Alpha, we're often doing this kind of algorithm discovery, saying we need an algorithm that does such and such a thing, then go search a trillion algorithms in this computational universe to find one that satisfies the constraints that we're looking for. So that's that's been a thing that is sort of a very powerful idea in creating, in sort of being able to discover algorithms. We're used to, as humans, we're used to engineering things sort of step by step, figuring out what's true, and setting up our engineering structures by sort of building them incrementally, whether it's us doing it as engineers, whether it's natural selection, kind of progressively, incrementally changing some feature of a creature to make the next one. What happens when you go out into this computational universe of all possibilities is you get to discover all kinds of things that you never anticipated were there. You get to discover a lot of very sort of clever things that we never imagined. There's a lot of implications of going and looking at this computational universe of possibilities. It kind of changes the economics of creativity. It means that you can kind of mass customize things by just going out into this computational universe and finding things which are structures and objects which are useful for particular purposes. And so this has been done quite a bit in art, music, and so on. It's also, as I say, very, very useful in all kinds of technology. It's also useful for creating structures of things. And for example, one direction that's emerging these days is for things like algorithmic drugs and molecular computers and so on. Being able to sort of go to this computational universe of possibilities and identify things which one had not anticipated were there. Well, among other things, these ideas in science and the details of the science sort of make possible the Wolfram language, Wolfram Alpha. There's a lot of other sort of implications, but to talk a little bit about Wolfram Alpha, Wolfram language, I mean, I view one of the things that's a question in the world is how should one program things? And I view sort of Wolfram Alpha as a zeroth programming language for people. This doesn't really require any programming at all, it just requires knowing human natural language. I view the Wolfram language as a really good first programming language. It's a programming language that both has sort of all modern paradigms built in and has all this knowledge and actual algorithmic content built in. And it's a first language that's good, I think, for lots of kinds of people, including kids and so on. As we make it more readily accessible and deployable through the various cloud things that we're doing, I think we will see some interesting things happen. So I might mention on sort of the opposite end of the spectrum from the tiny programs and the things for kids and so on, the sort of corporate enterprise type applications. Wolfram Alpha is, we've been doing lots of sort of custom versions of Wolfram Alpha where we take kind of data from within an organization and combine it with knowledge from the world at large to produce something where you can kind of ask questions about that organization and get results. It's kind of the challenge is to go sort of from the big data state of an organization to sort of the big knowledge state. And it's the objective is to kind of create computable companies. One can also create computable cities, computable countries, where sort of the idea is if there's a question that can be answered on the basis of knowledge and data that's been accumulated, make it automatic to do that. Well, in general, we've been doing lots of things with data science. We're sort of creating a general data analytics platform using all of the various pieces of technology that we have here. We've also been much involved in connecting that data platform to devices, and one of the things you'll see in the next 6 months or so is interactions with a zillion different kinds of devices for all sorts of different purposes, kind of feeding data into the technology stack that we have, being able to get linguistic questions answered through Wolfram Alpha type technology, being able to get sort of elaborate interactive reports through CDF technology, and so on. So one of the areas that's kind of fun that I've pursued a bit on the data side is personal analytics. I guess that many years ago, I've been interested in data for a long time, so many years ago I started collecting, what's happening here? I started collecting data about myself. And so, for example, there's a dot for every piece of email I've sent in the last 25 years. Or, for instance, let's see, there's a dot for every keystroke typed in the last little while. There's a sort of an aggregated plot of my kind of average daily schedule for the last year or so. It changes progressively over time. So these are things, this is sort of personal analytics that one can do by sort of feeding in data about oneself. And I was sort of embarrassed to discover about a year ago that I think I may be the human who's collected more data on themselves than anybody else. It was not what I really would have expected, but I've just been interested in data for a long time. Well, for people who haven't already been doing this, there are places where sort of data gets left by people. One of them is something like Facebook, A few months ago, we started a personal analytics for Facebook system that feeds into Wolfram Alpha. One of the things we did actually a few weeks ago, we realized, okay, millions of people have used this. Let's actually, we had set it up so that we got anonymized data from these people. We also had a data donor program, which quite a lot of people have signed up for. We said, okay, let's find out what we can figure out, and sort of a little data science exercise. So starting about 3 weeks ago, we decided to take a look at some of the data that we had from this Facebook analysis, and let me see that I can show you what we got. I just posted a blog actually about this, and if I can only find looking for it here, there we go. Sorry, this is what happens if I show things which are absolutely hot off the press. Well, let me see. Let's see, here we go. Okay. All right, let me show you a few things that we learned from this exercise in doing data science from Facebook. So these are sort of some typical networks from data donors. We can also ask things like, what's the distribution of the number of friends that people have, for example, for our collection of people, and for people in sort of slightly broader Facebook population. We can ask things like, how does the number of friends that people have change with their Facebook age? So we see people, I think this is partly a reflection of just the fact that Facebook hasn't been around that long. We can ask things like, how do the ages of people's friends, how do they relate to the age of the person themselves? So we see that sort of for young ages, the ages of friends are very closely correlated with the age of the person themselves. As they get older, it spreads out a bit. We can see that here. Another thing we can ask is, what about relationship status that people quote on Facebook? And we can see that it starts off with most people being single, and then it ends up after a while that most people say they're married, and we can look at how that sort of evolves over time for people. It's kind of remarkable to me how similar this looks to kind of doing, the chemical species in a chemical reaction. It's kind of, the humans work in an aggregate in the same kind of way. A surprise for me was comparing this with what you get from, for example, the US Census Bureau, asking the question, how does the data that you have from Facebook compare with what's been found by actually doing explicit census surveys, and apart from the weird, 13-year-old kids saying that they're married type thing, apart from that sort of glitch, the thing tracks surprisingly well. So you can ask all kinds of things about how the number of friends people have vary with the country they live in. You can ask things like, how do people typically migrate between countries? You can see that on the basis of sort of hometown versus current residence. It's kind of interesting to see all the flow from between different places. Let's see, Netherlands has a small flow to the US, it looks like here. Then you can go through and look at all sorts of properties of networks. Another thing you can do is to ask, okay, what do people talk about on Facebook? What are, can you categorize with topic modeling and so on the things that people discuss? And it's sort of interesting to see, as a function of age, how people's discussion of different kinds of things varies. The reddish line is women, the blue one is men. You see how health changes with age, or you could look at something like politics. People get progressively more interested in politics as they get older, it seems. They get less interested in video games as they get older, and so on. What I think is more, so there's a lot of interesting things that one can do, sort of mining this social universe from Facebook. To me, actually, one of the things that was most interesting about this was generating all the stuff from the raw data was really easy using the tools that we built with the Wolfram language and Wolfram Alpha and so on. And this only took a very small amount of time to do, which was encouraging. So just let me just say one more thing. For me personally, the last couple of days I've been in Europe, and I wanted to visit a place that I've been meaning to visit for about 20 years, which was Hanover, Germany, which is the place where Gottfried Leibniz lived. And so I went to the archive, to Gottfried Leibniz's archive. And the thing that's interesting about Leibniz, he lived about 300 years ago, he died in 1716. The thing that's interesting about Leibniz is he almost did the things that I've been trying to do for the last 30 years, except he was 300 years too early. And it was kind of interesting to see, for example, let's see, you can pick up some of his actual writings, and there Leibniz was trying to figure out how to make sort of a universal system that could be used to encode all the knowledge in the world and turn it into logic, and then be able to actually automatically compute from it. His version of automatically computing from things was this object here, which was the first 4-function calculator. It never actually completely really worked in Leibniz's lifetime. He worked on it for about 30 years. But that was kind of the technology that Leibniz had available 300 years ago. And when you read what he writes about sort of getting libraries constructed that would include all the world's knowledge and being able to turn it into a characteristica universalis, a universal language from which one could compute what was true and solve all legal cases and answer all arguments and so on. It's sort of charmingly similar to the kinds of things that I've tried to do, except that he was 300 years too early. And so I think it's an interesting thing to kind of think about as we see what we are doing in the present world to try and understand what things we understand how to do with computation, for example, but we don't quite have the ambient technology to do it. And one of the things, for example, with Wolfram Alpha was that I worried a lot which decade. I'd been thinking about doing something like Wolfram Alpha for about 30 years, and the question was, in which decade was it going to be possible to actually do this? And what we've seen is that, yes, it is possible to make a computational knowledge engine in this decade. There are other things to be done with computation in subsequent decades, making use of kind of the same core ideas, many involving medicine and other kinds of things that I think will be pretty important for the future of history. Anyway, I should stop there, so thank you very much.
Intelligent questions after a keynote, but I'll just stick to a question. When I look at Wolfram Alpha and the stuff you built and compare to Google, I get the impression that Google is about search, obviously, and search almost seems to imply that you've lost something. When you look at Wolfram Alpha, I get the impression that it's more about the answers. It's even more about the answers than the questions. But that makes me wonder, do you see yourself as something that exists alongside of Google as a search engine, or will it one day replace it? Or how ambitious are you there? Would you say something about that?
I'm not very ambitious. I just like building interesting things. But the objectives of what we're doing are somewhat different from the objectives of a search engine. I mean, the idea of a search engine is the world has produced all this stuff on the web. Now go see whether the particular keywords you type in match things that exist on the web, give you pointers to those things, then say, go read those things and see if you can figure out what you want to know from those things. We're trying to do something much more ambitious, much crazier, much more likely to be just plain impossible, which is to say, can we actually just answer? Can we actually just, for the particular thing you want to ask, just get an answer? Now, there's sort of a merger of these two things that starts to happen as you start to think about kind of the web itself. We deal with lots of data sets for lots of kinds of things. So, if you ask a question about a person, for example, in Wolfram Alpha, you'll see, the number of hits to that person's Wikipedia page, as a function of time. It's kind of an interesting proxy for how interested the world has been in that person. And you start seeing sort of, there are pieces of where you, and now we've got all these things with Facebook and so on, you're starting to see these places where sort of the computational knowledge paradigm intersects with kind of the what's on the web question. But we're not emphasizing what Google has done very successfully, which is to say, do a keyword search, find what's on the web, give you those things to read. That's sort of not what we're doing. We're also more interested in sort of the coming situation of sensors feeding in data and so on, and being able to make sense of those kinds of things, rather than what's been put on the web. I mean, you have to understand there's somewhere between 5 and 10 billion meaningful pages on the web, and actually it's not growing that fast. And that's a certain set of things that our civilization has put out there. We're sort of interested in the things which can happen in the future with kind of other sources of data and so on.
So there was, I don't remember who said it, somebody in search, and he said, we made a fundamental mistake when we built the first search engine by giving people just a search field, and sort of implying that just entering one word would answer their question. And that's another thing I noticed when I visit Wolfram Alpha, it's almost intimidating, because I feel there's a lot of knowledge there, but I've got the search field, and I feel like, you know, everybody's staring at me, and I gotta write down something smart, because then I'll get a smart answer, and that can be intimidating. So, is there a way to solve that?
Well, that's probably one of our most fundamental problems, is how do people know what's there? Because there's a lot, you know, and typically when people, for example, use search engines, they have certain patterns in their heads, like they search for people's names, they search for, you know, places, they search for, you know, they see an error message on their computer, they search for the text of that. People have a certain number of patterns. It's the same kind of way with Wolfram Alpha, and, you know, people learn, you know, we progressively see people learn different kinds of patterns, but there's a lot more there. So how do we give them all the stuff that's there? I think what's coming is kind of a different approach to the delivery of knowledge. I mean, the current version of the delivery of knowledge is kind of request-based knowledge delivery. That is, you think of something you want to know about, you type it in, you say it to your phone, whatever else, and then you get knowledge provided to you. I think what's coming is much more preemptive knowledge delivery, where on the basis of personal analytics, on the basis of lots of history about you, on the basis of kind of situational information about where you are and what you're doing and so on, and what data is coming in from sensors and so on, then provide what knowledge you should want to know. And that's something where there's a lot of algorithms and heuristics and so on to figure out what's useful to give you, because, you know, the biggest challenge will be not to give you too much. Because, you know, in any particular situation, there'll be tons of stuff that can be said. One of the things that we've achieved, actually, with Wolfram Alpha, that we've been surprisingly successful with, I think, is generating these reports that say, sort of give not just the answer, but lots of other information. But we typically have tons and tons of information that we could include. And we've done, I think, a pretty decent job of sort of figuring out what are the things that we actually should include. And that's using that kind of technology we expect to be able to do a lot of sort of preemptive knowledge delivery, where we're sort of telling people what they should be interested in, what we think they'll be interested in, based on their history and based on the situation they're in, and based on our large sort of supply of knowledge and computation that we can do. And I think the computations get real interesting because it's not really just a question. When you're in a particular situation with particular history, that situation, that history will be unique. It will never have happened before. It won't be the case that it's just good enough to say, okay, let's give you a page from Wikipedia or something about this. It will be something where you actually have to custom compute what is worth saying, and that's a place where you kind of need to use this sort of computational knowledge stack, and that's an area that we're pretty interested in.
Awesome. Well, thank you very much. Another round of applause.